Well, thank you very much, Chris, for the invite to come and talk at the Appleton Space Conference 2021. I'm just delighted to have the opportunity to talk about what's happening with all our missions on Mars. What's going on Mars today is really well displayed in this image, in that we have many different nations participating in a variety of orbiters. And as you can see, with the orbiters and those surface assets like Curiosity, Insight, Perseverance, the Ingenuity helicopter, and the Chinese lander and rover, Mars has more going on right now than any other planet besides Earth. We're accumulating enormous amounts of data. What I'd like to do today is concentrate on a few things that are happening most recently with the Perseverance rover and the Ingenuity helicopter. But before I do that, I need to sort of set the stage, give you a little background on what we have learned over the last many years of exploring Mars. One of the exciting things that has occurred just in the last couple years with our ground penetrating radar, or shallow radar charade on the Mars Reconnaissance Orbiter, is that we've uncovered what we believe is a buried glacier. Now, this is understandable in the sense that even though it's at mid-latitudes, the obliquity, or the axis of rotation of Mars, really swings from a handful of degrees to as much as 45 degrees. And therefore, the northern polar caps and southern polar caps, their positions change on the planet. And what we believe we see here is during one of those times when there was a high obliquity, and therefore ice accumulating at these latitudes, which then have an overburden, and that overburden provides an opportunity for this glacier to be maintained. It doesn't sublimate, in other words. In the very thin atmosphere of Mars, the water on the surface will sublimate very quickly and very easily. There is an enormous amount of water here. In some places, it's 750 meters thick, and it's as big as the state of New Mexico. Now, in addition to that, another radar on the ESA Mars Express mission will go down deeper, and we've been able to find what we think is a large liquid water lake down at about 1.5 kilometers. It's actually a very large lake. This is really telling us that there's probably, like Earth, an underground aquifer system. So not only do we see ice in water, water and ice form on the surface, but we see liquid water below the surface. Now, in addition to that, we have all our landed assets. Here's an overview of the location of the landers and rovers. Those in blue are the ones that are currently operating. This is on a Mercator projection of Mars. And so in this projection, we have colored the topography in altitude. So the reds and the whites are the high altitude, and the blues and the deeper blue or purples are the very low altitudes. This also tells us where water would exist on Mars over long periods of time. For instance, the blue area in the north, 2/3 of that northern hemisphere, is a lowland, and this is where an ancient ocean for Mars would occur. And we know that Mars had a significant amount of water in its past. There's indications of past water all over the place that we're finding from our ground assets, and this had been going on for many years, even from the Viking era. Now, what we see then is at the ancient shoreline in the area of just the greens and the yellows. This is where Curiosity is. This is where Perseverance is. These are important areas because, you know, we find that there is an enormous amount of land-water interactions. In fact, in this set of images of Gale Crater, where indeed Curiosity has landed, we see it's right there on the ancient shoreline. That right-hand panel shows this Gale Crater with this huge central peak we call Mount Sharp. We've landed in this crater, and indeed the crater wall is right on that ancient shoreline, and we see areas such as what's displayed on the left of material that has been moved by water action and creating an alluvial fan at some time in its history, where the water is poured over from that ancient ocean and into Gale Crater. Now, the black oval or ellipse is our landing ellipse, and we landed pretty close to being in the center of this landing ellipse for Curiosity, and that occurred in 2011, and it's still going strong, making spectacular measurements. Now, one of the things that Curiosity is doing is beginning the path to crawl up Mount Sharp. And what we see is we see the hematite mineral. This is an iron oxide, that is produced in the action of water. We also then see clay regions. Clays are really clearly important water-land interactions. And as we get up into the sulfate areas, that's currently where Curiosity is right now. And so it has really made quite the journey, and we'll continue on up Mount Sharp. Now, what has Curiosity found? It's really gave us a number of fantastic discoveries. Here's Curiosity on the crater floor of Mount Sharp early on in its mission. And what it has is a pulverizing drill. That pulverizing drill will create a hole about the size of diameter of a small coin and about 1.5 centimeters. And here are actually the first two holes in terms of what Curiosity drilled on Mars in Gale Crater. And this actually was quite a surprise. We see the red patina of the oxidized surface of Mars. That's what's given Mars, the famous red planet look. But just below the surface, we see gray Mars. We see Mars a completely different composition than what we see just at the top surface. In fact, Curiosity has the ability to scoop this material up, bring it into the rover, and really analyze it. And what we found has been absolutely spectacular. The mineralogy indicates really a sustained interaction with liquid water flowing into this region for millions of years, perhaps 100 million years or more. Key chemical ingredients for life are also present, like carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. The soils are moist, and they actually have nitrates in them. So this has been a tremendous set of discoveries. But Curiosity is also looking for much more complex organic molecules. And recently it's found a really spectacular set of complex organic molecules like benzene and propane. But these are connected into a larger macromolecule set, which are kerogens. And on Earth, typical organic constituents of kerogens are algae and woody plant material. So this tells us that the environment, even though it's bathed in cosmic rays, there are certain situations for which these complex organic molecules can stay together that we then can interrogate and look at, perhaps getting a window on the past conditions on Mars and whether there was life there or not. Now, in addition to that, Curiosity has the ability to take in the atmosphere. Now, the atmosphere of Mars is pretty thin. Its average is about 6 or 7 millibar. Here on Earth, we're at 1,000 millibar. So you can see it's less than 1%. of the Earth's atmosphere, dominated by carbon dioxide. But there's also nitrogen and other trace gases like argon. But we also find bursts of methane on Mars. Curiosity has the ability to, on a regular basis, sniff that atmosphere and look for methane. It has found methane every time it's done that above its background, whether it's during the winter or during the summer. However, we also notice a seasonal variation in that. For instance, in the summer, we find indeed much more quantities of methane. Now, these are down in the 710 parts per billion, so it's very much a trace gas. But methane, of course, the importance of that is trying to understand, is that generated by biology or abiotic processes, okay? And indeed, methane can be done by either one of those. We haven't figured out yet which one it is, and perhaps it's a combination of both. In addition to the methane observations from Curiosity, we also have a spectacular lander called InSight. In this InSight, which has a wonderful seismometer, the best seismometer we've ever put down on the surface of Mars, really teasing out the structure of the planet, developed by not only the French but the UK. It has a fabulous range in terms of its ability to see Mars quakes. Now, of course, from Mars quakes, and we have been observing them since InSight landed in November of 2018, it's observed more than 700 events. And these events have enabled it to tease out the size of the core, the mantle, and the crust. In addition, we find that there are some reasonably mild quakes. These are associated with this volcanic region, which is straight east of where InSight has landed. Now, in addition, InSight also has a weather station associated with it. And the weather station on InSight and Curiosity, and now also Perseverance, along with our orbiters, allow us to look at the global circulation of the atmosphere of Mars. Now, we feed that data into the Mars Climate Modeling Center that NASA manages at Ames. Here's an overview of indeed the dust and water and CO2 atmosphere compositions over a year. And so indeed, we can predict sort of the weather on Mars. You know, the winds can actually get as high as 125 miles per hour. What we just see is the potential during the Southern Hemisphere summer for global dust events. So the modeling that we've been doing now is really pretty extensive because we have this rich set of data. Well, what have we really learned from all these observations is indeed, as I mentioned, Mars started out as a blue planet. Early on in its history, it looked like Earth. Indeed, it had a significant amount of water, more than a kilometer in depth in the northern hemisphere, we believe. We even see indications of tsunamis that hit the ancient shoreline of Mars. But something happened about 3 billion years ago where Mars went through a rapid climate change and became the arid planet pretty much that we know today. The water cycle of evaporation, transport, and then rain was broken, and indeed evaporation then led to dissociation of the water molecules, and then without a magnetic field, which it lost somewhere in this time frame. We know from the MAVEN observations and orbiter that we have at Mars now that the solar wind strips this oxygen out of the atmosphere. And so over these last several billion years, Mars has stayed pretty static in the sense that when we get down to the right places and start interrogating these areas, we're really going back in time in that early era of Mars, 3 billion years ago, interrogating a lot of the wind, atmosphere, ocean, land interactions that we are so familiar with here on Earth happening at such a large scale on the planet Mars. Well, what are these discoveries really leading up to? Well, it's telling us that ancient life, may have existed there. The potential for that seems to increase in every one of these sets of observations that we're making. We see lots of signs of ancient water, both surface and underground. In fact, as I mentioned, there might be currently today a fair amount of underground water in liquid form. Past geological environment that really had the reasonable potential to have preserved the evidence of life had it existed. These detection of complex organics really also increased because we can find them in the soils. They seem to be preserved under certain circumstances. And of course, those are fingerprints of potentially ancient life. But we need to make major changes and continue on this line of teasing out what's happening at Mars. And so this means we really can figure out where to go on Mars to get to the right places, and therefore really seek in a much more aggressive way the samples so necessary that tell us about whether Mars had ancient life or not, and what those ancient conditions were, how the climate changed, and so many other things. This requires a Mars sample return. And that's what Perseverance is really all about. So Perseverance is our latest rover, and it went to Jezero crater. Here is Jezero crater in the context of the area around it. We see the Isidis Basin, very large impact that occurred 3.9 or so billion years ago, right at that ancient shoreline. The ocean was in Utopia Planitia, as you can see here. And then about 100 million years later, at about 3.8 billion years, another impact happened, forming the Jezero crater. Now here's an expansion of the Jezero crater, and this is a fantastic place. What we see in the upper left, of course, is a river valley. So water was flowing rapidly into Jezero crater, and the crater was filling up. And indeed, it broke its wall, its crater wall on the northeast side, where the water then flowed into the basin and then into the ocean. So in the meantime, what was happening is the rapidly flowing water would indeed hit the still water that was sitting in Jezero crater and began dropping its silt. And so we see a delta that we want to go to and interrogate. And so here's the landing area that we selected for Perseverance. And when we now look from orbit, we can understand the changes in mineralogy. Here's our landing ellipse. We wanted to land just outside of the delta. Now the delta has been built up over hundreds of millions of years, we believe, at least 100 million years in event, and is about 65 meters in width. In height, with a width of about 10 kilometers. So this is really an extensive region. From orbit, we can tease out some of the mineralogy, at least areas where there's the dominant mineralogy. And of course, with Perseverance, we're going to be able to tell much more about these regions, because we'll have ground truth. We'll get the information necessary to really be able to say, yes, this is indeed basaltic material, et cetera, et cetera. Now, river deltas here on Earth are just a tremendously important habitable environment. You know, we can go to our own ancient river valleys and we can tease out a lot of past life, life that has lived in the river, come down, died, and is part of the silt. This is a perfect area, we think, to be able to interrogate, create samples with Perseverance, whose main objective is to go to these areas and create samples for later return. We also know that in these areas where there's interactions between oceans and our our shorelines here on Earth, you know, some of the oldest life are these microbial mats, these stromatolites, and indeed they form a rock record here on Earth that we want to be able to understand how those stromatolites form, live, die, what the rock record looks like, and how we might be able to identify similar structures on Mars. And Perseverance definitely has the capability to do that. So indeed, in February, we landed Perseverance just outside this delta, this huge delta. This is through the entry, descent, and landing capability that I'm sure many of you have heard about. It takes about 7 minutes to go from the top of the atmosphere, you know, and we're running at about 7.5 kilometers per second. And in 7 minutes, we're moving centimeters per second as we set the rover down on the surface with this mobile sky crane, which then we break the ropes and the sky crane moves away. Now, we also had some spectacular opportunities with the Mars Reconnaissance Orbiter during one of its passes while Perseverance was making its landing. And here you see it. You actually see the small circle in the center. That's actually the landing site where Perseverance ends up. And then you can see in the blown up fashion, the parachute and the capsule just before we drop the heat shield and the rover falls out to then land on the surface of the planet. And then here it is being lowered down by the sky crane to a Octavia E. Butler landing site, following our tradition of wonderful science fiction writers naming landing sites after them. And indeed, this was a spectacular and perfect landing. Now, Perseverance has a suite of spectacular instruments, all the way from ground penetrating radars, which will be so important when we get up on top of the delta and begin to look at the stratigraphy. We're assuming that, you know, water will be flowing. These things will build up over time. Hopefully we'll be able to find eras for which there might have been a lot of flow and then less flow over periods of time, giving us some sort of history information. That would be wonderful if that would be possible. Also, we have instruments that like SuperCam that fire lasers that will then heat a small area on a rock, which of course excites the atoms. We're able then with our spectroscopy instruments to be able to interrogate that and get concepts on the composition, rock composition. Same thing with Pixel, which is at the end of the arm. The arm has several fabulous instruments. Pixel does this in X-ray. You know, we'll zap a rock and we can get the mineralogy. We also then have the opportunity to core the rock. The cores are about the size of a chalkboard chalk. And for those younger scientists and others in the audience that have never used a chalkboard chalk, I'll say it's about the size of a large Crayola crayon. So then that is put in a metal sleeve, We hang on to these as we make several of them and then drop them in piles. Right now, we have 5 samples that we have created, 5 sample tubes. 4 rock samples and an atmospheric sample has been created. We haven't dropped them yet, but we're on our way over the next several months to really thoroughly interrogate the crater floor where we're at, and then begin the process of going up the delta and begin to look at what's up there. Now, why is the rock record so important? Well, if we look at what's going on here at Earth, there's over 5,000 minerals, distinct minerals on the Earth, for which about 330 or more really are known to be formed by interaction with organic matter, okay? And there's several already on Mars that sometimes form biologically with the biology here on Earth. And so the rock record is going to be incredibly important for us to understand how the climate may have changed so rapidly and provide some sort of information on the potential for past life, and if we're lucky, may even find evidence for past life on Mars. So once we create these cores, that's part of the activities that we're currently doing. We're going to need to return them, which is now generating a new discussion and a new set of missions that I'll also talk about how we're going to move into the future. Now, in addition to the fabulous instruments on the rover that allow us to look at the geology, look at astrobiology potential, and then also the coring and therefore caching the rock samples, we actually have another experiment on the Perseverance rover that gives us a great indication of what happens as humans are potentially on the surface in the future. And this is with our Moxie instrument. This is the Mars Oxygen In Situ Resource Utilization Experiment. This is designed to bring in CO2, zap it, pop off an oxygen. Oxygen then will, free oxygens will recombine and create molecular oxygen and carbon monoxide. We now have the ability to test that process on Mars with Moxie, and it's working fantastic. With the unit that we have, it's already made during its individual runs 6 to 10 grams of propellant grade O2 per hour from the atmospheric CO2. And in the future, since this works so well as if it's in the laboratory, we want to be able to also scale it up. And we think we can do that as discussed here. Now, in addition to the Human Exploration Instrument, we also have what we call technology demonstration instrument, and it's really a helicopter. It's the Ingenuity helicopter. It sat underneath the belly pan of the rover. We dropped the pan and dropped, indeed, the helicopter drove away. And then we had an opportunity to actually fly it. Now, here's a little image, a movie rather, taken from Perseverance during the time of the helicopter's first flight. This has really been a fantastic step forward. Our first vehicle to fly on another planet. We've done now the 5 test flights. They have worked perfectly. We had some surprises with wind buffering and frame rates and everything else, but we've sorted all that out. And indeed, it's worked perfectly. And so currently, Ingenuity has done 16 flights and has really done a fabulous job, not only once it passed its first 5 flights, to begin the process of scouting out regions and places where Perseverance may be able to go or couldn't possibly go, but giving us other information that we'd never get. So that's worked extremely well. So finally, I want to tell you about how we're going to get the samples back. The next new push is through the sample return campaign, for which Perseverance creates those samples, drops them off, and we'll have a mission we'll launch probably in the 2026 timeframe that will land. That's our M1 mission in this diagram. That mission will contain a fetch rover in addition to a Mars ascent vehicle. The fetch rover will gather those key sample caches, bringing them back to the ascent vehicle. The Mars ascent vehicle then will be erected. The samples will be deposited in orbit, and then M2, that next big mission, well, we'll get into orbit, hunt those samples down, acquire them, and bring them back to Earth. So we have a spectacular, indeed, set of material we want to bring back. It'll come to a biosafety level 4 facility for initial analysis. And our hope is that we won't find any problems via planetary protection, that we'll eventually be able to release these samples to the broader community, and therefore really get a more in-depth understanding of Mars and how it evolved, and answer the question whether Mars had life on it in its past or not. So thank you very much. Let me turn it back over to you, Chris.
Okay. Thank you very much, Jim. That was a fascinating talk. We've got some, or at least one question, Jim. Can you see it?
Let me get out of this and stop sharing my screen. Okay.
So do you recall that some researchers have claimed evidence for stromalite islands on Mars? Is there any plan to visit these locations for future sample returns? And also, are there any plans to repeat the Viking experiments, which showed evidence of methanogenic reactions?
Yeah, great question. So right now, we believe Perseverance is absolutely in the best place where ancient life could have occurred. We're really, as I mentioned, going back in time 3 billion years or 3.5 billion years in the area that we're currently at. That is indeed the time that stromatolites started here on Earth. Now, there's no indication so far, but we've only been on the surface of the planet for the last 8 or so months of finding structures that look like stromatolites. But we also haven't extensively interrogated the delta yet. What we've really done is interrogated the floor of the crater, and the samples that we've created are from rocks and material that's in the floor. And in fact, there's a volcanic area at the top, just west of the river, that ancient river, for which we believe that volcanic area also percolated water and is another wonderful place, like hot springs, where we might be able to find indications of life. So no, we haven't found any stromatolites yet, but it'd be great if we do. Now, the second part of your question is on the Viking experiments. Now, there's been, of course, a lot of discussion on whether Viking had indications of current life. And the label release experiment was one that gave a positive indication, but the other experiments, the 2 other experiments, did not. And so the project decided, well, that means we're not going to announce that we have found life. Now, that also, meant that there's a big push to fly this instrument again. NASA chose not to fly the instrument again and get the same result. Okay, that's what we would expect happen. But through the samples that we bring back and the environment that we're in, bringing those back, we can do much more, well beyond the labeled release experiment, in our laboratories. And we can really understand then what reactions were occurring, and whether it was biological or abiotic processes that were occurring. And so I think we'll get a better handle of putting the context of the label release experiment information when we get the samples in our laboratory.
Okay, and that's when do we expect that? It's a long time now, isn't it?
We want the samples back by the end of this decade.
End of this decade. Okay, that's good. Okay, so there's a question about what rovers might reveal about the geology and specifically how climate change took place on Mars. And I guess whether we could learn any lessons about what we're doing.
I believe strongly that our understanding of climate change is indeed informed by looking at our planets. You know, what's happened on Venus can happen on Earth, all right? What's happened on Mars could happen on Earth in a different way, not from a runaway greenhouse effect that we see on Venus, but the fact that Mars no longer has its magnetic field. And so we're looking at solar wind, ionospheric, atmospheric interactions, and all the processes that are occurring right there, right now on the planet Mars. Well, the Earth's example is that we have a magnetic field, but there's also indication that the magnetic field of the Earth is decreasing and the pole is starting to move. These, we believe, are a telltale sign that we may be in for a magnetic reversal or a flip. Now, when the flip occurs, the field gets very small, and then it's reestablished with the opposite polarity that it has today. And that means from a geological record, we see that flip over many, many times, but we don't know from a geological perspective if we'll be without a magnetic field for 100 years, 1,000 years, or 10,000 years. Because the rock record says it's, you know, there's the flip, all right? And then we have a field for 100,000 or more years. We can see that in the rock record. So indeed, by studying what we see going on at Mars, that's got to be what will happen to Earth. And because we're closer to the sun, the solar wind will be more intense, not only in volume, but in many other ways. During those time periods where we'll have a magnetic reversal going on. So comparative planetology is really important for us to fold that into our understanding.
Okay, that's interesting. The magnetic field seems to be the key to all of this, doesn't it? But,
maybe so. Yeah. I'd like to think so. I'm a magnetospheric physicist, okay. But you know, wishing doesn't make it so. We really need the observations.
Okay. So then we have a question about, could you expand on how the methane measurements were obtained?
Yeah, so one part of the instrument called SAM, a sample analysis on Mars, is that they have a port that will then bring in the methane, and then we stimulate it, and from the analysis, we can determine the amount of methane in parts per billion. So the details of exactly how that's done, I'll have to refer you to what we do in the SAM instrument. But the key to that is we haven't accumulated enough of it for us to be able to tease out the isotopes of carbon. You know, methane's carbon and hydrogen. Carbon has carbon 12, 13, and 14. Carbon 12, 13, and 14 has a natural proportion between them. If there's something that's generated abiotically, one would expect to see, you know, that reflect some sort of proportion that's similar to what you see in nature without life for methane with carbon 12, carbon 13, and 14. But life is a really wonderful discriminator in carbon. Life loves, that we know, life that we know, okay, loves carbon 12. And carbon 12, then, if we see a glut of carbon 12, that may give us another indication that the methane is generated biologically and not abiotically.
Yeah, and people certainly use those methods in human breath analysis to look at,
yes,
it's like whether there's excessive biological activity going on when you've got sepsis and things like that. So interesting. Okay, so the next question is, how do you plan to protect the samples from Mars before arriving at Earth, really? I mean, I guess
there's
that's
been,
a two-part question, isn't it? How do you make sure that you don't damage them, and also how do you protect us from them?
oh yeah, all that's been major parts of discussions for quite a while. But let me give you an overview of where we are in that analysis. We're going to put the samples in a container that then is sealed, and then sealed again when it's picked up by the spacecraft in orbit. So it will be double sealed. And then the plan is when we drop it on the Earth, it will go to our place in Utah that we love to use to drop samples. We've done that several times now before. And we will not use a parachute. The plan is for the samples to crash into the Earth. And the reason for that is we want to be able to build a system and test it that has that capability and not depend on a parachute working. So once those samples land, and then of course their orientation is important to preserve the provenience of the sample itself in that system, then we will bring it into a biosafety level 4 facility. And therefore we'll have some initial set of analysis equipment that will then be also in that facility that will open the samples and begin the interrogation. What's critical also to know is the set of information that we take on the rover before we take the sample is also of a critical set of information. We talk about all the material, the mineralogy, the composition on the surface. We actually, after we pull a sample out, we can even take our laser and run down the inside of the hole and look at some of the elemental composition of the rock over the length of that entire sample by interrogating the hole itself. That information is going to be carried with the sample. And so we'll then also have a process for which we'll go through what samples we open first, the kind of analysis that we'll do, and then ensure from a planetary protection purpose that we can release the samples to a broader community for analysis, for further analysis.
Okay, well, the questions are coming thick and fast. So how do you plan to get the samples off the surface of Mars into orbit? Can't be straight.
Yeah, we're gonna use a rocket. We're gonna have a fetch rover that will bring them over to a Mars ascent vehicle.
Okay.
Load up the sample container, seal it, erect the rocket, and blast it off the surface. And then the rocket is going to deposit the sample, the initial sample container in orbit. And then another spacecraft will hunt that down, get into orbit, and then find it and bring it in and encapsulate it again. So there's nothing on the surface of Mars that is touched, that the container is touched, that will have access from the outside. It will be completely sealed off from Mars itself by this double bagging, so to speak.
Fantastic. I mean, that's so with all the experience we're going to get with space debris removal, you'll be going and effectively removing space debris from Mars. Is that what you're saying? I think you're.
Well, we in terms of debris on Mars, as we roll along, we actually see a variety of meteorites that come down.
Okay.
Because of Mars's thin atmosphere, Mars meteorites are there when we find them. And those are really good because they will shake the surface, and InSight will see them. Okay. And that also produces signals. So not only do we see Mars quakes generated by Mars itself, particularly in this Elysium area where there are volcanic, where there may be some still active volcanism going on at some level, or the ground is settling from cooling, from the eventual cooling. Not sure what's happening there. That's where we're seeing these modest little earthquakes that actually occur once a year. So that we find after the last couple of years for it being on surface. We also will be measuring close impacts from meteorites.
Okay, so there's two related questions. The methane and minerals found so far may or may not be biological. So what's the minimum signal that you'd expect to see that would help you decide whether or not life was there or past or present?
Yeah, well, what we need to do is be able to accumulate a lot of methane. Right now, the most methane we've gotten in one gulp is about 22 parts per billion. For curiosity to really begin to look at the isotopes, we need probably closer to 100 parts per billion. And then we could just begin to look at the isotope analysis. So we haven't seen those big bursts. Now you have to recognize that 95% of the methane we see here on Earth has been generated biologically, we believe, and but that doesn't mean that's the case at Mars. But it also could be ancient methane that's been trapped underneath the surface. It doesn't have to be the biology that's currently there. It could be trapped, and then during the summer season, when the sun shines on the surface and warms it up, allowing methane to percolate through because it sublimates a little water layer that seems to be pervasive in the crust. And then comes out in greater abundance, and that's when we capture it and look at it. So we have a lot to do before we can really determine.
So you think it might be a little
biological
similar to the problem we have with the thawing tundra and
yeah,
methane emissions from past biological activity?
Right.
Yeah. Okay. That's fascinating. Okay, so we've got a couple more questions. One from Libby Jackson saying, when you say they're starting to see signs of the magnetic flip, what are the timescales for the reduction?
Oh, here on Earth?
Yes, so here on Earth, yeah.
Yeah. So I was just using the analogy that our own magnetic field may be in the process of flipping. Magnetospheric physicists are talking about this now. We see the field decreasing. All right, so the magnetic field strength of the Earth is decreasing. And the pole is starting to move. Some predictions are that our pole in the northern hemisphere, which turns out to be a southward seeking pole, may be in Paris in 50 years. Well, we can, in our lifetime, then we'll be seeing that movement of the pole. From all the modeling and all the understanding of the geology and the rock record that we've done, that's an indication that the field is flipping. The decrease of the field and the movement of the pole. So we'll just have to see if that happens or not.
Okay, and we have one final question, and that is about InSight. What science, if any, are you expecting that you might be able to do with Ingenuity? With Ingenuity. Apologies.
Yeah, with Ingenuity. Well, Ingenuity was a test. It was can we fly on another planet or not? Now we know we can. Now the discussion is, how big can Ingenuity get? The next generation of Ingenuity. Now, right now, that helicopter is about 4 pounds, and we believe we can fly something as much as 40 pounds. A factor of 10. Now that's a much larger system, but now we're in an era where we actually could have much more sophisticated instrumentation. So if we just tag on the methane concept, let's say we have a methane sniffer on that next generation helicopter, putting it in an area where we believe methane may be leaking through the surface, and then go back and forth and create an image, a two-dimensional image of methane measurements, looking for whether there's a location in that grid, where there's a lot more methane coming up. Perhaps it's connected to an underground aquifer or something, for which then the next thing we'd want to do is be able to go there and drill down. Another great thing for the helicopter would be to go into these lava tubes. We know Mars has caves, and we know Mars has lava tubes. And in fact, some of the roofs on some of these lava tubes have collapsed. It'd be absolutely spectacular to fly a helicopter into one and make a variety of measurements: pressure, temperature, and then image the area, looking for potential biology that may be hanging on the inside of these lava tube walls. Our understanding of these lava tubes is that there's probably a steady temperature and pressure throughout the day and night in these lava tubes. If that's the case, that's pretty spectacular. On the surface of Mars, the temperature ranges 170 degrees Fahrenheit change in one day. If you can go into a lava tube and you have a constant temperature, then human exploration is much easier on the surface by using that as the habitat, and be able then to know how much energy you need to come up with a temperature for humans to survive on the planet's surface.
Okay, so it's really opening up a lot of new possibilities for you.
It is, yeah,
and,
it is.
I guess you're also getting much more science out of the rover that's associated with by being able to target interesting science locations. So rather
Correct.
than missing things, you can go around and you can home in on them and find them.
Yeah, and what we also think is important is the helicopter flies over regions that we know we would never take Perseverance to. They're too rough.
Okay.
And so it's really getting a good look at what's happening in those areas at really high resolution that give us a little insight as to how this whole area is created and how it's evolved over time.
Okay, well, thank you.
Yeah.
All right, well, thank you very much, Jim. That was an absolutely fascinating talk.
Great.
I confess I didn't appreciate just how much was going on in studying Mars. I've obviously not been getting out much, and I need to find out more, because it is absolutely fascinating. So I'm sure on behalf of everybody, thank you very much for a very inspiring talk, and we look forward to all the successes that are to come, and the new missions, and getting those samples back finally.
Thank you very much. My pleasure.
Okay, we look forward to meeting you in the UK very soon.